Okay, so now that we talked about parametric surfaces and oriented surfaces, what I would like to do is just go through what a surface integral of a function of three variables would look like. So in essence, we have learned that for calculating the surface area of a particular region, what we do is we basically get the oriented surface, which is basically the magnitude of the cross product of the parametric surface differentiated with respect to the two parameters that describe it, and then times the element of area dA. When we have a function inside of that integral, all we need to do is, well, each of those coordinates are going to become a function of those two new parameters u and v, and then we're simply going to multiply that by this magnitude, and then we're going to integrate with respect to the element dA. So in a more general sense, the parametric surface can be written in terms of any two arbitrary parameters u and v, simply by substituting every single one of the variables in it by a function of those two parameters. So in this video, we're going to be looking at this very simple example. So we have the function x squared, and we want to compute the surface integral of it, or evaluate it on the following surface. So the surface is a sphere of radius 1. So once again, it makes sense to use spherical coordinates because we have a spherical surface. Now, as we discussed before, we would have the radius of the sphere just comes in here, but because it is 1 in this case, we just don't write it at all. And we can represent each of those coordinates in terms of the two parameters that characterize that surface, which are the angle phi and the angle theta. And then, of course, we're also given that the element of area is going to be d phi d theta, and the reason for that is that on a sphere, if you take a chunk of the surface area, this is going to be described by two infinitesimal changes. One is going to be the change in angle d phi, and the other one is going to be the change in angle d theta. The area is going to be a rectangle, so basically just multiply those two to get the infinitesimal element of area. Now, at this point, what we need to do is we need to write down the parametric surface. So this is going to be in terms of those two parameters, phi and theta. So now what we're going to do is we're going to put x, y, and z here. So this one is going to be sine phi cosine of theta. This one is going to be sine phi sine theta. And the last one is going to be cosine of phi. And now the whole idea is to calculate this magnitude here. So the cross product of the derivative with respect to phi cross with r theta. So those are the partial derivative with respect to each of those variables. And we know that it doesn't matter in which order we take the cross product because we're taking the magnitude of that, so we're always going to get the same value. Now, we already found what this was for the spherical coordinates in the previous example. We found that it was r squared times sine phi. But in this case, the radius is given as 1, so this is actually just going to be sine phi. And we know this was a rather long derivation, so I'm not going to derive it again because we just did it in the previous video. But this is essentially what this quantity is going to become. So now all we need to do is plug in everything in here. Now the last thing we need is to know what are the limits on theta and phi. Well, since we're taking the entire spherical surface, they're just going to correspond to the full rotations here. So we have this, and then we have phi going from 0 to pi. So now we can write the surface integral of x squared ds as follows. This is going to be 0 to pi, 0 pi. Now we're going to put this here inside of x squared. So this is going to be sine squared phi cosine squared theta. And now we're going to multiply it by this quantity. So that's going to be sine phi again. And then d phi d theta. So this is going to be the integral that we're going to evaluate. So let's see what we get from here. So we're going to have, well, obviously we should multiply this by that. So we're going to get the following. We're going to have, this is going to become 0 to 2 pi. And notice that we can now pretty much just separate this. So we're going to have this here. Since we have constant limits on both integrals, we can separate this into two integrals. So we're going to have cosine squared theta d theta. So that's going to be this times the integral from 0 to pi of sine cubed phi d phi. And the reason we can do this is because we have constant limits on both integrals. So what we can do now is we can evaluate this integral first, then this one, and then we multiply the results together. So let's do just that. So for this one, we can use a simple trigonometric substitution. So hopefully you are quite familiar with this one because we have used it quite a lot in this series already. So it's going to be 1 plus cosine 2 theta, and all of this times 1 over 2 the theta. So now we're going to have half of theta plus 1 over 2 sine of 2 theta. This is from 0 to 2 pi. And now let's see what we get. Well, we're going to get half 2 pi. This is actually going to be 0 for both cases, so we don't even need to include it. Minus 0. And then this is just going to be pi. So that's the first integral here. Now for the second one, let's write it down here. So we have 0 pi of sine cubed phi d phi. Now for this kind of trigonometry, when we have an odd power of sine or cosine, what we can do is the following. We can rewrite this as sine squared phi times sine phi d phi. And now we're going to change this by an expression containing cosine. And the reason for that is that we're going to be able to use substitution to evaluate the integral then. So this is going to be this 1 minus cosine square of phi sine phi d phi. And now we can perform a substitution. So if we say u equals to cosine of phi, then du is going to be equal to minus sine phi times d phi. So now if we essentially just put a minus here, so let's just rewrite the integral here, minus 0 to pi. So we're going to have on here, we're going to have 1 minus u squared. And then this is just going to be du. And remember, we put a minus here because we put a minus on the inside as well, so that this will be exactly equal to du. So now we just proceed to integrate this. So we're going to have u minus u cubed over 3, 0 to pi. But before we put in the limits, we need to actually substitute back for the original function. So this is going to be cosine of phi minus cosine cubed phi over 3 from 0 to pi. So let's see what this gives us. So we're going to get, okay, so cosine of pi, that's 1 minus 1 over 3. And now if we put 0 in, actually cosine of pi is minus 1. So what am I talking about? It should be minus 1 here. We have minus 1 squared, that's still minus 1, that becomes a plus. And then we have 0 here, so this is going to be minus 1. And then if we put 0 in here, that becomes plus 1, so that's minus 1 over 3. Okay, and let's see what this gives us. Oh yeah, of course, I forgot the negative sign here, so this should be here. So this should actually go all the way here. So we're going to have minus. Alright, so here we're going to have minus 1, that's minus 2. And we're going to have plus 2 over 3. And what's this going to give us? Well, this is going to be 2 minus 2 over 3. So let's see. This is 6 on 3 minus 2 on 3, which is 4 on 3. So now that we have that, we have our surface integral. It's going to be the product of those two results. So we can write x squared ds. And this is going to be equal to, so the first result we got was pi, so this is this integral. So we're going to have pi here times the second result, which is just 4 on 3. And then that means that our final result is going to be 4 pi on 3. So that's our final answer for that surface integral. So hopefully you can see that you can use oriented surfaces, basically just a parametric surface, to compute the surface integral of a function of 3 variables. In this case, it was just a function of 1 variable, but you can see that this extends to any general case. And this is how you calculate a surface integral using a parametric surface.